All right, y'all. Today we're going to be talking about log functions, not exponential functions, but log functions. Remember last class we talked about, or 2 classes ago, we talked about how log functions are the inverse of exponential functions, and we write them with our log and then whatever that base is. Now, our transformation variables are going to work exactly the same for log as they do for exponentials. So if I'm wanting to transform our log functions, my a, b, c, and d are going to be in the exact same spot. So a, b, c, and d. And they should do the exact same thing. D is going to be our up and down shift. C is going to be our left and right shift. B is going to be our horizontal stretch compression. As well as our reflection across Y. And then A, of course, is our vertical stretch, vertical compression, and reflection across X. Okay. Now, the specific function we're going to be focusing on, or we're going to start off with our parent function, is log base 2. So let's graph this in our function so we can kind of get a picture of the graph and then some of those key features. So go ahead and grab your TI-84, your little yellow calculator. And if we want to be able to graph this, y'all, we can go into our y equals. And then to get that log where I can get any base I want, notice I have my log button down here and my natural log button. Log is base 10, and that ln for natural log is base e. But I want to use log base 2. So if we hit the math button and then arrow all the way down to option A, you see this log all caps base. If I click that, it will give me a logarithm where I can put any base in. And I want to put in a base of 2. And then, of course, I want to add my x. And when I hit graph, it will graph that nice logarithmic function. Now, a couple things we know about our logarithmic function, y'all. We know that it has a vertical asymptote at x equals 0. We discovered that last time with our inverse. And we know that it should be crossing right there at 1, 0. That's that inverse from 0, 1 for our exponential function. If we wanted to be able to actually grab out some nice table values, we can go here to second table. And we get lots of gross ones, but we can see some nice ones: 1, 0, 2, 1, 4, 2, and 8, 3. So let's use those for our actual graph. So adding our points in, we got 0, 1, 2, and 3 for our y values, and 1, 2, 4, and 8 for our x values. And adding those on to our actual graph: 1, 0, 2, 1, 4, 2, and 8, 3. And we can connect the dots to get our nice logarithmic shape. And like we said, we do have a vertical asymptote right here, which of course I want to be dotted and not solid. But we have a vertical asymptote at x equals 0. That kind of frames our graph. And you might remember those points because those points are the same points that we get for our exponential function, but they've just been inverse. So all of our y values for our exponential is now our x's, and our x's are now our y's. So let's talk about some of our key features. Our graphing point is going to be that 1, 0. Our vertical asymptote is our x equals 0. Our domain this time is our 0 to infinity. And our range is our all real numbers, or negative infinity to infinity. So asymptote became x equals instead of y equals, and our domain and range switched from our inverse function. Okay. Now, Just like our transformations could affect our exponential functions, our transformations can also affect our logarithmic functions, but just like everything's switched, it's going to be slightly different. So for our graphing point this time, still affected by C and D, but it's actually affected by our B value instead of our A value. And that's because our X is the one that has that 1. So for our graphing point, it will be B plus or minus C, and then whatever our D value is. So that's a little bit different from what we've seen before with our exponentials, but once again, everything's flipped. So exponentials was C and then A plus or minus D. Our logs is B plus or minus C and then D. Likewise, our vertical asymptote, because it would shift left or right, it's now going to be our C value. So a little different because our exponentials was the D value. For our domain could be swayed by our C value shifting it left and right, or our B value, if we were to have some kind of reflection across Y, of course, that would switch our domain. But our range this time is what's going to remain unchanged when we do each of our transformations. So everything with logs should feel familiar from exponents. Everything is just switched around a little bit. So let's actually put some transformations into practice. So let's look at A, for example, 5. We have a log base 2 of x plus 3 minus 4. So let's identify some transformations. We can see this plus 3 on the inside is going to shift us to the left by 3 because our C is always opposite. And then this minus 4 at the end will shift us down by 4 because D is exactly what it should be. So that's going to change our graphing point, which normally is this 0, 1 right here. Or not 0, 1, sorry, 1, 0. That's going to shift us over by 3, so over to -2, and down by 4. So -2, -4 is our new graphing point. Everything else is going to stay the same, though. So we would go up and over by 1, then up and over by 2, and then up and over by 4. And we can see that nice logarithmic shape. And of course, our shift left by 3 would shift our vertical asymptote over to -3, which helps frame our logarithmic function as it gets closer and closer, but doesn't cross or touch. Okay, so definitely comparing the two, looks like we shifted left by 3 and down by 4. Going through our key features real quick, our domain this time is the one that's going to change. So it shifted to -3 to infinity. Our range, of course, is going to stay unchanged. And then our asymptote shifted over to x equals -3. Let's do one more together. So looking at B, we have 4 log base 2 of x minus 1 plus 3. So that 4 in the front would be a vertical stretch of 4. That minus 1 on the inside would be a shift right by 1 because it's always opposite. And then our plus 3 would shift us up by 3. So let's go ahead and add our asymptote on first this time. It is going to be at 1 because we shifted to the right by 1. Then for our graphing point, for exponentials, our A affected our graphing point, but it's not going to affect our graphing point for log. So the only thing that would affect our log is a B, C, or D value. We don't have a B value, but we do have C and D. So we're going to shift to the right by 1. So from 1, 0 to 2, 0, and then up 3. So we're up here at 2, 3. And then for my next point, usually I'd go up and over 1, but we're going to go up by 4. 1, 2, 3, 4. And over by 1 for that next point. And if I wanted to get a third point, y'all, I'm going to be off my graph. So just like we talked about with exponentials, y'all, as long as you can do asymptote and graphing point, that second or that third point, it's nice if we can get them, but they're not always going to fit on our graph, so we don't need to worry about them too much. And so we can see we've definitely shifted to the right and up and stretched out that logarithmic function by a factor of 4. So how is this going to change some of my key features? Where our domain shifted to the right, so 1 to infinity. Our range never changes, all real numbers. And then our asymptote would be x equals 1. Okay, so go ahead and do this last one, C, on your own. So go ahead and pause me, and then I'll go over C. All right, let's talk about C. So we should see a reflection across x, that negative in the front, a shift left by 3 because of that plus 3, and then a shift down by 4 because of that minus 4. That's going to be almost the same as a, except that reflection. But remember, we don't reflect across the x-axis if we've shifted down by 4. We're essentially shifting across y equals 4 because of that shift down by 4. So that's why it looks like it's just reflected across that graphing point right here. So we're going down from our graphing point of -2, -4 instead of up from our graphing point. So domain, range, and asymptote would be exactly the same as A for C. So a little bit of a trick with our reflection, but remember, if you have a reflection and a shift, you're not necessarily reflecting over the axis anymore. You're reflecting over that shifted axis. All right, y'all, let's flip this over onto the back and let's do some harder bases. So just like we did for exponentials, we could have different bases for our logarithms, and the bases we're going to focus on is base 10 and base e. And you notice for k of x and h of x, they don't have bases written. If we have a log without a base, that means it is base 10. And to help us remember, we can add in that 10. And if we have a natural log without a base, that means it's base e. So we can write that in just so we don't forget. And for our log, let's pull those points. If you forgot, remember for exponential, for our logarithm, it was 0, 1, and then 1, 10. So for our log base 10, it would be 1, 0, and 10, 1 for our x and y values. And we can see those same points here on the graph as well. So same points, but we've switched x and y from its exponential counterpart. So let's identify some transformations. Our transformation of 3 would be a vertical stretch by 3 since it's an a value in the front. And this plus 2 on the inside would be a shift left by 2. Since we have it inside, it's a c value. So let's transform these points just to help us out a little bit. So our left by 2 would subtract 2 from our x values. So that would give us a new set of x values of -1 because 1 minus 2 is -1, and 8 because 10 minus 2 is 8. And then for my y values, my a is going to affect my y values, and I multiply a, so 0 times 3 would still be 0, but 1 times 3 would be equal to 3. So we get the new points -1, 0, and 8, 3. So -1, 0 here, 8, 3 up here. And we can add in our asymptote, which based on our c value, we know is going to be at -2. And that helps frame our logarithmic function just a little bit as we connect our dots there. So comparing the two from our parent function to our new function, we can see we shifted left by 2 and stretched out by a factor of 3. So it's always good to compare parent to our transformed so you can make sure you have everything correctly. Okay, so finishing up with our key features, y'all, should be the same as our parent function for log base 2. But of course, our transformations domain is going to shift to the left by 2, so -2 to infinity. Our range is always all real numbers, and our asymptote's that new asymptote of -2. So x equals -2. Hey, we got one graph left, and it's our base e, which base e can be a doozy, but if you remember, our points were 0, 1, and then 1, e, but we said that e is about 2.7. So let's use that 2.7 again today, but of course, it's going to be inversed. So our x values and our y values are now 1, 0, and 2.7, 1. So we're just switching those values. Okay, and we can see those bear out. We have that 1, 0 on our graph, and then it looks like about 2.7 is where we're hitting that 1. So that definitely tracks and makes sense. Okay, our asymptotes, our transformations that we see, we have a 3 here in the front, so that's going to be a vertical stretch of 3. We have a -2 on the inside, so opposite, that would be a right by 2. And then we have a -4 at the end, so exactly what it says, so that would be a down by 4. So applying them to our points, let's transform them and get some new points. So our c value is going to apply to our x. So 1 plus 2 would be equal to 3. 2.7 plus 2 would be equal to 4.7. So while we don't like that 2.7 number, y'all, it should be relatively straightforward to do some simple math with just that value. And then for 0 and 1, we'd multiply by 3 first. So 0 times 3 is 0 still, but then minus 4 would move us to negative 4. And then 1 times 3 is 3, but then minus 4 would move us to negative 1. So our new points are 3 comma negative 4 and 4.7 comma negative 1. So that would give us some points to work off of. So 3 comma negative 4, 4.7, which is a little less than 5 comma negative 1. And then last but not least, to help frame it, we can add in our asymptote, which we know is at positive 2 because of our C value. And then we can connect our dots. And if you notice, y'all, even though I probably could have fit another one on our graph, it might be a little bit close. I didn't go past those first 2 points. So remember, if you can do the graphing point and even just getting that second point on there plus the asymptote can really pull your exponential or your log together and make it really pretty simple to graph those transformations correctly. Okay, so let's finish up by doing some key features. So our domain for this would be 2 to infinity because we shifted to the right by 2. Our range is always all real numbers. And then our asymptote is that new x equals 2 because of that shift to the right by 2. Okay, I'm going to let you do this last section on your own, but we're going to write some functions based on the information given. So for A and for B, I've told you which base the log function is. I just need you to identify which transformation has occurred. So go ahead and pause me and try and do A and B on your own. All right, y'all, on example 4 for A, the only thing they've told us is that our new vertical asymptote is at x equals negative 3. That means our C value, we've shifted to the left by 3. It's going to be opposite, though, when we add it in. So it is log base 2x plus 3 for our actual equation. And then on B, we have log base 3 of x. Looking at our table of values, we can see our original graphing point of 1 comma 0 stayed 1 comma 0. So we haven't shifted left or right, and that tells us we do not have any sort of horizontal stretch or horizontal compression because that x value didn't change. But what did change is we started at 3 comma 1 and 1/3 comma negative 1, and both of those changed to half, so negative 1/2 and positive 1/2. So that tells us we are vertically compressing, we're squishing it together. So that would be a 1/2 for our A value in front of our log base 3 of x. All right, y'all. That's really it for log functions. They're very, very similar to exponential functions, just that inverse or that reverse. Go ahead and do some of the practice, the jigsaw, and don't forget to take your exit ticket, okay?